For positive real numbers s, let tau of s denote the set of all obtuse triangles that have area s and two sides with lengths 4 and 10. The set of all s for which tau of s is non-empty, but all triangles in tau s are congruent, is an interval, a to b, half-open interval. Find a squared plus b squared. Okay. So, in general, I need to think about a triangle, an obtuse triangle, so that means it has a right angle, or sorry, it has an angle greater than 90 degrees. The area equals s, and it has two sides with lengths 4 and 10. And we're also concerned with for what values, basically we're asking for what values of s. Well, I should say L1 equals 4, L2 equals 10. So two of the side lengths are given as 4 and 10. We don't know which side lengths, and we don't know which is, we don't know which is which. Of course, well, let's figure out what we're being asked for exactly. For what values of s is there essentially only one such triangle? That's what we're being asked for, because we want there to exist triangles. We want values of s such that there is a triangle satisfying this. But the second condition here is that all triangles in tau s are congruent. Essentially means that there's pretty much only one triangle which has these side lengths and the area s. We want to find all values of s which satisfy this. Okay. Let's start. So it's an obtuse triangle, but let's actually let's draw a right triangle just to sort of get our bearings here and figure out what can be done. So if I just arbitrarily say that the lengths here are 4, if I say it's 4 and 10 like that, okay, so clearly then s has to be equal to 20. Right, the area of this is base times height over 2, which is 20. And this side length is root 116. Okay, now if I think about, so let's fix that side there at 4. If I grab this point, or maybe I should think about it, if I grab this point and move it to the right and it's fix this side length of 10, and just take this point and start to swing it downward. Then we have 4 and we 10 and 10, and it becomes an obtuse angle here, but instantly the area gets smaller. Okay, so if I call this theta, then the area as a function of theta is, it's what? It's, is it 20 sine theta? Let's draw this triangle. Okay, so if that's theta, yeah, the y, the height of this is sine theta. Okay, however, is there, the question though is there another triangle with a side length of 4 and 10 with the same area that is not congruent to this one? So the alternative way of parameterizing a triangle like this is let's think of it this way. Let's draw another right triangle just to sort of figure out some stuff here. But let's say it's like this, 4 and 10. So now, what is the other side? 10 squared minus 4 squared is equal to h squared. 100 minus 16, 84. And the area of this is h over 2. No, it's not. It's 2h. It's 4 times h over 2 is 2h. So this area is I think I see what's happening in this problem, like what we sort of need to figure out exactly. So this area is 2h. That's 2 root 84. Okay. And now, if I think about, again, swinging this point down, but keeping these sides fixed, eventually what's going to happen is positive numbers. The set of all obtuse triangles that have area S. Okay. So, yeah, let me try and explain how I'm going to piece this all together. This area, 2 times root 84, that is less than this, right? This is clearly a bigger triangle than this one. Okay, they're both right triangles. Oops. So what that means is, if S is equal to 20, I mean, it's obtuse. This is why because this is a right angle here in this exact triangle, that's why there's a half open interval of what we're doing, because technically S can't actually be equal 20. This is not an obtuse triangle, but it can get arbitrarily close to 20. So as we decrease, if S is equal to 20, if we allow right triangles, if S is equal to 20, this would be the only one. This would be the only triangle allowed. As we decrease S, we have to swing this point down like that, and we move into a triangle something like that. But eventually, S decreases enough that we can now make a triangle with this area with that configuration. Okay, so so basically, what I think is like the key here is, you know, S must be in the interval A to B as specified in the problem if we want only one triangle to satisfy these conditions, where A is equal to 2 root 84 and B is equal to 20. Okay. So let me just go through this logic again. If we allow right-angled triangles, then when S is 20, this is the only triangle that satisfies the conditions. As we decrease S, we start to move this point down like that. We decrease S, we fix 4 and 10, we're fine. But if we decrease S down as low as 2 root 84, now there is suddenly a different triangle which gives the same area. And there will now be 2 triangles which allow for this type of construction. Okay, so we're asked to compute a squared plus b squared. So this is going to be 4 times 84 plus 400. What's 84 times 4? 336. So I get 336 plus 400, and that's 736. Okay, I'm pretty confident in this. Maybe there are some other strange exceptional cases that I'm not taking into account. I'm usually not a fan of these types of geometry problems. If I were writing this contest for real, I would skip this question and maybe come back to it later. Although this isn't exactly the style of geometry problem that normally drives me crazy. Usually it's the ones where you just have to memorize some kind of, or have some obscure formula or relation between triangles and circles and so on that you never actually use in any kind of non-contest setting. I think what I've done here works though. So that'll be my answer, 736. But if I find a mistake, then I'll let you know, and I'll let you know what the real answer is. Thanks for watching.